So I get the opportunity today to talk about searching for habitability at the extremes, and it's a really great benefit to me to go directly after Danny Glavin's talk, because that was the perfect introduction for what I want to talk about. And this Mars 2020 sample return mission, going to pick up samples, put it in its rover backpack, and bring them back to Earth, the question becomes, how do you pick a good sample if you're looking for a sample that might be indicative of the habitability, past or present, on that location? And of course, Mars is not the only potentially habitable environment, past or present, in the solar system. We've also got the icy moons of Jupiter and Saturn. And yesterday we learned a lot from Sarah Horst about Titan and its unique organic atmosphere. But we haven't heard yet much about the icy moons of Europa and Enceladus. So let's look at those a little more closely. These icy moons have an ice crust, that's water ice for the crust. Beneath that, there's a liquid water ocean that's in direct contact with a rocky core. And because most of my slides are pretty dark, I've tried to turn these monitors so that you can see a little bit better. And basically, anywhere you get liquid water interacting with rock on a planetary scale, you'll get subduction, gravitational pull of that water down into the rock. That will then lead to exothermic reactions between the water and the rock, oxidizing the rock, reducing things in the water fluid. That'll heat it up to about 100 degrees. This is called serpentinization because that's one of the main reactions that's occurring during this time. And that effluent will get forced back up out to the that interface between the water and the rock. These are called alkaline hydrothermal vent systems because that also raises the pH of the effluent. So now we've got a great pH and redox gradient from the ocean water to that effluent. We've also got a thermal gradient anywhere we find these on Earth. It's an excellent place for booming populations of extremophiles. And these have been implicated in the emergence of life in certain models for the emergence of life on Earth. So on Enceladus, where we have the benefit of free samples spewing out into space, 435 kilometers, with these massive geyser systems out of the south pole of Enceladus. Cassini flew through there, and there is indications of ongoing active hydrothermal activity at the base of its subsurface ocean. We have indications that similar processes are likely happening on Europa, but we have yet to get the direct data to confirm any of that. Another thing that we think of whenever we think of habitability, and the reason why I'm not trying to sit here and define habitability in terms of a long list is, you'll see, we might not fully understand what parameters contribute to habitability yet, but we do know that all life as we know it is made of organic chemistry. And so, as Danny Glavin made very clear, we have now found organic molecules on Mars, so there may be an organic inventory with which to support life there. Out at the icy moons, when Cassini flew through the plume of Enceladus, it had an ion-neutral mass spectrometer, INMS, and that detected not only small organic molecules, but recent data mining from the that mass spectra indicates that there are higher molecular weight organic species, and these are the peaks that contribute to that, indicating that there might be a fragmentation pattern indicative of larger organic molecules that were outside of the mass range of that instrument. And the instrument was never designed to detect large organic molecules because we just didn't simply know that we might find them. Okay, so since flying to these areas around the solar system is rather expensive, it's a lot cheaper to use locations on Earth that are terrestrial analogs of these extremes in order to better understand whether those systems could actually be habitable. On Earth, good analogs for Mars include things like the Atacama Desert, which is the oldest and driest desert on Earth, and it's got UV sterilization down to a certain depth, not nearly as deep as on Mars, as Danny Glavin was discussing earlier. And it's also got perchlorates generated in the surface. And so it serves as a very good terrestrial analog, not just biologically, but also to test samples. Other terrestrial analogs for Mars where extant life could potentially continue to exist to this day include the lava tube caves, where life could have retreated to and be protected from radiation. And additionally, at the lower latitudes, these could have a pressure high enough to be above the triple point of water and support liquid water today. Hydrothermal systems have been proposed. At least they would have existed in the past, but perhaps not persisting into the present. For the icy moons, we have a number of excellent terrestrial analogs, including glaciers and subglacial lakes like Blood Falls, shown here. We've got the ice shelf and alkaline hydrothermal vents. Due to some evidence suggesting that Europa might be very highly saline, we're interested in these deep hypersaline anoxic basins. And there are a number of different studies ongoing to these various locations. And here I've just posted a couple. We're involved in this Rise Up with Brittany Schmidt out of Georgia Tech to build instrumentation to go on an under ice submarine. And we've got an instrument that's being deployed currently in Antarctica this field season. We're also interested in these oceans across space and time, which is also PI'd by Brittany Schmidt out of Georgia Tech. Now, what I'll talk about for the rest of today is this field site that I didn't list here because we're going to discuss it in so much more detail. And those are the Icelandic lava fields. So just a reminder, this is what we're thinking about here. We're trying to be an analog of a Mars 2020 type of a rover mission and try to really understand what are the best ways, given the instrumentation that has been selected for that mission, to pick up samples to put in our backpack and bring them home. So how have we done these sorts of work in the past? And I want to give you a quick intro to how do typical field campaigns run. First, let's look at the Atacama Desert. This is the oldest, driest desert. There have been a number of studies done there. I'm going to show this one because this is out of my PhD lab, where we looked at both exposed duricrust at the very surface and some shielded duricrust, where we simply moved a rock away and an analog of like a rover wheel scraping away a rock. And we also dug down, similar to having a scraper. And what we found, unsurprisingly, is that the amounts of organics, in this case we were looking at amino acids, are significantly higher in that shielded duricrust, just a centimeter or two beneath the surface, than at the surface. And this was actually at our detection limits. It is very challenging to get cleaner water than 10 parts per billion, as Jamie Alcila showed us earlier. And the information we can get, if we can get that subsurface sample, is really great, because with that we were able to do a chiral analysis and, based on the racemization rates of amino acids, accurately date the age of the desert to the last major rain event. Danny also talked about how depth sampling is crucial, so I'm not going to harp on this much more. It's not just Mars where we would like this, but also Europa, where I showed this image earlier. You'll probably see it better on the screens, where we've got these charged particles and ionizing radiation coming in from the magnetosphere of Jupiter. And so depth profiling is an incredibly important and common technique, and it's relatively well understood. The other one are these transects across gradients, and in this case I'm showing, again from the Atacama Desert, where the Dries et al. Group went and sampled across various altitudes, 400, 700, 987, 1315, all the way out into the height of the Andes. And so across this transect, multiple things are changing, but they're attempting to control just for altitude and go in and calculate the total organic compound, total organic content, and the culture forming units, number of those. And what you'll see in this is it appears, although with a table of data, it's really hard to ascertain any correlations. It appears that at the higher altitudes are where we get more organics and more cells. What is not clear from this plot, however, is the additional correlation between fog at the coast going through the Yungay region, which is this incredibly dry region due to the geographical constraints here that pull the rain out before you get here, up into the Andes where the rain gets, where you actually get some rain again. And so there are these multiple correlative issues that we have to think about whenever we do a transect. And so a single transect may not be the best way to do this unless we're going to get all of the data out of a transect. Additionally, at each one of these locations, only one sample was selected. And everything we know about biology in these exceptionally low biomass areas suggests that it is stochastic in nature. And we know this even from walking through the forest. Here you get a mushroom, and here you don't. If you're walking through the forest and you miss that mushroom by 10 centimeters, you're going to get a very low fungal count whenever you go into your biological analysis. Okay, so now let's come back to this image one more time. I promise it's the last time I'll show it, because this is what the rest of this talk is going to be based on, is this analog mission. And it's a short vignette into how do these field explorations actually go and what can we do with all of the data. So FELDSPAR, field exploration and life detection sampling for planetary analog research, fortunately shortens to an acronym that is also the primary mineral in our samples. We're doing this with high fidelity and a number of key areas to Mars missions, from how do you select a sample with landing site sample selection, landing site selection using orbital data, through rover driving operations down to individual sample site selection, whether you get it from here or 10 centimeters away. We're also trying to be relatively high fidelity in our technology, where we use a suite of geochemical measurements that give us, if not the exact same instrumentation type data, analogous data to what could be obtained by the instrument suite that was selected for the Mars 2020 mission. After that, we're very interested in how do we fully characterize the habitability of a sample. What are these measurements that map on to predict high biological activity? And for this, I'm not suggesting that ATP and DNA are good biomarkers. If you want to talk about biomarkers, that's a completely different wing of my group. Today we're talking about habitability and field work. And on Earth, though, due to the vast conservation of ATP as an energy currency molecule and DNA for information storage, we can use these as proxy for metabolic health of the community and total biomass of the community. And we understand that those measures are not perfect, they're just proxies. And then finally with the science, I'd actually like to talk about the science as we talk about the site itself. So let's look at the site. We're looking at Iceland. And Iceland is great because it's got that fire and ice mix where we get volcanoes in a very cold environment. Down in the south, we've got a volcano, the Eyjafjallajökull eruption that was associated with the infamous shutdown of European air traffic in 2010, 2011. And that's where we get the Fimmvörðuháls lava field. Near that, we've also got Mælifell, which is a recently deglaciated plain. I'm not going to talk much more about them because we'll actually be focusing more on these northern sites, Hólahrún and Dynjandishur. Let's take a closer look at them. Hólahrún, this is another very dark image. You might be better off looking at the smaller one on the screen. It's a volcano that erupted in 2015, cooled off enough to allow scientific travel in 2016. And this is one of these fissure volcanoes where the lava kind of oozed out, unlike Eyjafjallajökull, which explosively erupted. So it's got a relatively small cinder cone and a number of different geochemical gradients that were preserved there due to the way that the lava came out. My team was one of the first to go out on this volcano after scientific travel was allowed. And we were fortunate enough to find right next door to Hólahrún this Dynjandishur, which is a alluvial plain kept barren apparently via mechanical weathering and resurfacing of the region. And it has been largely surfaced by particulate out of the Hólahrún magmatic chamber. And so the overall geochemistry of the unaltered material in Holocrone matches well with this alluvial plain. And of course, closer up images of our Fembodohas and Mailafet Lysande. We're not going to talk much more about them. We'll just dim them out. And let's think about the scientific questions that we'll look at up north. So one of our primary questions is, how do these geochemical factors influence the habitability of a sample? And then in order to find that out, we really would like to go in and explore how many samples and at what spatial distances are required in order to fully represent an area. And for that, Dingyusander is just perfect. To get to Dingyusander, and of course it wouldn't be a good field presentation if we didn't have some pretty pictures, we have to go a very long ways from civilization. Akideri is the nearest grocery store and gas station. It's about 6 hours away. There are no bridges. We need to have a Jeep with a snorkel to get to our site, and then we have to hike for a good long ways from the furthest that we can drive the car. Whenever we get there, we fly a quadcopter so that we can map the terrain over which we will be sampling. And our quadcopter footage looks kind of like this. Our sampling strategy, in order to obtain statistically significant sampling at the multiple spatial scales while still keeping the overall number of samples small, has been to collect in triplicate samples 100 meters apart. And that gives us an equilateral triangle. At the corners of each one of these triangles, we collect samples again in triplicate at 10-meter spacing. At the corners of each one of these triangles, we collect samples again at 1-meter spacing. And at the corners of each of those triangles, we collect samples with 10-centimeter spacing. And the benefit of this is that it's the minimum number of samples with which to obtain statistically significant data at these multiple spatial scales. It's so much more efficient than doing a rectilinear grid, a square grid across the vast array of this area. All right, before I go to the next one, I wanted to point out, we picked Dingyusander because it's an apparently homogeneous area. The geochemistry and grain size looks the same across everything. Of course, if you're looking at this image, you're saying, Amanda, you're crazy. There's dark stuff and light stuff. So to nail down whether that dark stuff and light stuff was actually different, we have a number of different handheld portable tools that we bring in the field with us. This is a handheld visible to near IR reflectance spectrometer, kind of an analog to CRISM. And that shows us, based on the band depths, that the only thing that's changing between that light and dark material is the degree of hydration. And in fact, we observe this in the field ourselves. Right after a rainstorm, Dingyusander is dark gray. As it dries out, the albedo completely changes and it becomes this bright silver. All right. We take these back to the lab and we do our ATP analysis next after we've gotten all of our in-field data. And this is a very simple assay. It's converting luciferin to the excited state of oxyluciferin using firefly luciferase that only happens in the presence of ATP, which is our limiting reagent. Oxyluciferin then decays to the ground state, emitting photons, which we detect. Now, before we look at the data, let's go back to our sampling strategy, because remember, we've got 3 times 3 times 3 times 3 samples. This is going to get confusing very quickly, so let's pay attention. We've got the different 100-meter spacing samples color-coded, red, blue, and green. Inside of each of these, we've got 10-centimeter or 10-meter spacing samples. And inside of that, we've got 1-meter triangles. At the 1-meter scale, we'll color-code it by dark red, medium red, pale red, which I think we have a word for called pink. Okay. All right. And at each one of these corners, we've got 3 samples. So what we should see, 3 dark red for each of the 10-centimeter spacings, 3 medium red, 3 light red. That should repeat for each one of this spot, this data spot, and this data spot, those 10-meter separated apexes. All right. That will cover all of the red, then we'll switch to blue, and we'll do the same thing again, and then we'll switch to green. I'm going to keep, and then we've got 1 kilometer spacing on top of that, so we'll do Dingyusander Site 1, Site 2, and Site 3. So we've got a lot of data here to look at. I'll keep that cartoon up here as we walk through this the first time. It looks like the green is the easiest to interpret. So these 3 greens are separated by 10 centimeters. That's all 1 meter from these 3 greens, which are all 1 meter from these 3 greens. This whole data set is 10 meters from this whole data set, which is 10 meters from this whole data set, which is 100 meters from the blue, which is 100 meters from the red, which is also 100 meters from the green, which is a kilometer from Dingy-Sonder Site 2, which is a kilometer from Dingy-Sonder Site 1. All right. Bar charts with error bars are a way to quickly visually inspect and estimate whether samples are statistically significantly similar or not. If the error bars overlap, they're the same number. If they're different numbers. So let's go through here and visually inspect and agree this is not the best way to do this. We'll do some better statistical analysis here in a second. Across Dingy-Sonder Site 1, we're seeing mild fluctuation. Many of these numbers are the same number. However, a couple of samples stick out. At this point, we're starting to get hints that perhaps there might be ways to select this set of samples rather than this set of samples. Once we get to Site 2, it becomes clear there must be a better way to sample than this random sampling, because even with 10 centimeter spacing, you can have a sample that has lots of ATP or very little ATP. Now this is telling us that we have to collect samples with 10 centimeter spacing if our terrain is like a Dingy-Sonder Site 2 in order to actually represent that sample, because it would be very easy to walk through here and actually to accidentally pick up this sample rather than that sample, and then you'd be taking home the one that does not have the best chance of hosting life. Let's zoom out, and here I'm going to switch to DNA data, which gives you a slightly different chart, to the 1 meter separation. So each one of these data points represents one of those 10 centimeter replicates. Each column here is one sample at 1 meter spacing from the next one over. And so this is actually not the same year. So it's a slightly different Dingy-Sonder Site 2 and Site 1, so don't expect this data to exactly map onto what we just looked at. So what we're looking at here, this blue line is the average of all of the data. And our statistical test here is how far away are the different individual data points from that average. And what we're observing is that there is a significant statistical difference for many of these samples. That's at the 1 meter scale. That's a little bit discouraging. Now we have to get 3 samples at 10 centimeters, 3 samples at 1 meter, and it's not that much better at 10 meters. Now we've got 3 times 3 times 3 samples just to represent Dingy-Sonder. There has to be a better way. And so we looked at some samples from Holochrun, and I'm just going to have to race through this because I think I'm getting very close to being completely out of time. So we went out, and this is another one where fun images. This is 2 in the morning because we have to finish all of our sampling before the glacial flood cuts off our exit route. And we collected this transect, and we were controlling for color here as we went from Dingy-Sonder to Vikersonder, which is a pumice plain. Lots of different things were changing across that color gradation, but we collected a very large number of different data sets. Not just ATP and DNA, but we also looked for bacterial DNA, moisture content, XRF, XRD, NIR, grain size, etc. We did a simple correlation analysis here, which plots out in red where things have an inverse correlation, and in blue where they have a positive correlation. And then we started looking at how can we plug these bits of data into a machine learning algorithm. And the first step here was to attempt to group samples. And when we use ATP content to group samples, the separation of samples is okay, but there's still some work remaining. We went back to the Dingy-Sonder samples with these new tools that allowed us to group that transect that we experimented with. And we're able to get a very good PCA grouping of the samples just based on our big data sets. And this gives us some hope that we could develop a machine learning model that would allow us to feed in a data set from a Mars 2020 instrument suite, and it would categorize that as habitable or not habitable with a percentage based on that prediction. So the future is to go back and get more data at Holocron, but to try to assemble data from all of these different field sites that people are working on and continue to do these analyses. There's interest in repeating this experiment in the Atacama Desert and throughout this oceans across space and time, and into the lava tube caves, which would be the most complementary data set to our volcanic suite in Iceland. With that, we're getting closer to figuring out where the best samples are in Iceland, hopefully on Mars. And of course, oh no, turn the sound off. He put horribly cheesy music over this. Students. Obviously, it's not just a single person, it's a big international team. So I have to thank them. I have to thank NASA for funding and for all of the other groups that gave us funding when we were still very early career, just students in love with the volcano. So thank you, and I think I may have time for like 2 questions.
We do have time for questions.
For the bacterial DNA, I was curious, was this a PCR-based method that you used? And what was the bacteria you focused on and why?
Okay, yes. So it was a bacterial DNA qPCR technique using the Zymo bacterial kit that's supposed to be relatively ubiquitous across bacterial strains, looking at, I think, the 16S rRNA cDNA. With that, you've hit on a good question, because we've also done an awful lot of sequencing and bioinformatics studies on these that simply don't necessarily feed into a discussion of habitability, but more of a discussion of the geomicrobiology of the area. So if you're interested in that, we have a paper that should be coming out soon.
So I guess related to that, if you were looking at an extraterrestrial sample, not on Earth, how would you envision adapting that method when you're looking for something that you don't know the sequence for?
Okay, so first off, let me be exceptionally clear. I do not think that DNA or ATP are the best biomarkers whenever we go out into space. It is challenging for me to believe or be able to support with data that life that has evolved under completely different chemical and thermodynamic conditions would select for the exact same energy currency molecule and the exact same base pairing structures, because it's got to have a completely different temperature regime under which it operates, and so it would have to pick different things. So I don't think that sequencing is a good method for looking for life on other planets. I rather think that looking for these astatistical distributions of amino acids and different structures. Danny Glavin showed a good slide near the end of the kerogens where you get those patterns of high intensity of things that are selected for biology that just don't come out of the Poisson distribution of an abiotic chemistry.
Thank you.
Yeah, there's a whole other set of what my lab does. I could talk about it for forever, and I'm a professor, so I can talk forever about anything.
Great, thank you.
Nope, cool.
I have a quick question. So on your actual on-site, you said you have some tools that you can do quick spectra, things like that. How do those compare to things that are on current rovers? What are the best ones that you would think would be ideal to have? And what are miniaturization and rad hard techniques or things that we should be doing?
Okay, so that is a very great question. In these basaltic tuffra environments, we've got order over very small scales, spatial scales, and they're very absorptive in general. So all of the light that comes in stays with that sample. It's not reflected back, so we don't get very good data out of the reflectance IR spectrometers, although we have a handheld one of those. And we don't get very good data from Raman, which relies on scattered light. So with the Raman tool, basically we have to turn up the laser power to try to jack up the signal, which then just leads to us ablating our sample and we get LIBS. So LIBS works very well on these samples. And for that, though, we have an XRF, which gives us the elemental composition. So that's an analog eventual or secondary data set rather than an analog primary data set. I like all of these tools, and I like the XRD. I think they give us very good data on that side, but I think organic characterization really needs to come in.